parity case, and you remember the potential here in this region between A and minus A along the x-axis here, one-dimensional case, and we're talking about one-dimensional delta wells. So the potential here is 0 outside the range A to minus A. It's V0, finite, right? Okay. And let's assume that the parity of your wave function u is even. Okay. So now, when the potential here is 0, you solve the Schrödinger time-independent equation. You'll get something in general form. U is A sine plus B cos. Well, sine is an odd function, so eliminate that, because we're dealing with even parity, let's say, and even where the wave function is even, because the potential is mirror symmetric. All right. So your wave function will have the form b cos alpha x. Right? This is revision. So that's the solution for your wave function u in region 2. And region 2 is this region here. Right? Region 1 is the left side, and region 3 is the right side, symmetric. Right? So in region, let's say region 1, your wave function takes this form. Right? Now this is all revision. Now, the general form would be like c exponent blah blah plus d exponent minus something. But we can eliminate the d on the right hand side because it blew up. Now remember, on the left hand side in region 1, x now is negative, so this does not blow up, so that's okay. All right. So the waveform in this region 1 takes this form, and in the region 3, it takes this form. Okay, so as x goes positive, large positive, this drops off to nothing. All right. So we know we have 3 forms of the wave function in the 3 regions, 1, 2, and 3. There's for region 2, that's for region 1, that's for region 3. Right? Now we're using alphas and betas. Now this is all revision. Alpha we defined as just square root of 2me. E's the energy, that's your eigenvalue for your st. Right? That's an allowed energy value over h bar squared, and beta something similar. Oh, we're also assuming the energy E, your eigenvalue, is less than V0. Right? If E is larger than V0, the particle can get out and then can go anywhere, and you no longer have a bound state. Right? So let's assume that E is less than V0. So it's sort of stuck in this potential well, in this, so that these act as a kind of barrier. Right? Now, how many of these energy states, how many of these E's, and hence we're assuming non-degenerate, right? Non-degenerate. So in other words, like a 1-to-1 for each energy or eigenvalue. There's only one eigenfunction, one wave function for that energy. So 1-to-1, right? So we're assuming non-degeneracy. Okay, so how many allowed energies here? How many bound states? That means wave functions, different wave functions in this area A, and to some extent in 1 and 3, but it drops off exponentially. All right. Well, you remember the gamma from several sessions ago, where we were drawing 2 sets of curves. One, the square root of gamma over x all squared minus 1, and the other set of curves was just the minus of cotangent of x, and where these curves intersected, where they cut. This is x here. This is x. The corresponding values of x, they gave you solutions for the allowed energy. Right? You find your x's from that x. You can calculate the allowed energy. So this also is revision. Now, if you ask the question, how many for a given gamma, where's gamma? Gamma's defined here, so also revision, right? So square root of 2m v naught a squared over h bar squared. Now, this is new. You've not seen this before, but do it for homework. It's just algebra. You know what alpha and beta are, right? Here's the definition of alpha and here's the definition of beta. So take the square root of alpha squared plus beta squared, so square this and square this, add them, square root the whole thing, multiply by a, and you will get gamma, right? So just prove that gamma, now gamma is that by definition, but gamma is also a times square root of alpha squared plus beta squared. So do that for homework, right? Now, if you want something tougher, if you want to know for a given gamma, remember as gamma increases, these curves here, they move more and more to the right. So there'll be more and more intersections of this gamma curve, if you like, with the cotangent curves. As it keeps moving to the right, it will intersect with more and more of these cotangent curves that go screaming up to infinity every pi, right? There'll be every pi, as x increases by pi each time, you add pi, you get another cotangent curve. So the more this moves to the right, more intersections, hence more allowed energies. Okay? So here's a formula. Think about it. Try and deduce it for yourself. I had to scratch my head a bit, but here's a bit more homework. All right? So the n here, so n here is the number of bound states. Bound just means you're inside the potential well. Bound in the sense you're trapped, you can't get out, right? You're bound. So the eigenfunctions, the wave functions, if you like, the u's, how many different u's can you get in this potential well for a given gamma, which is defined here. It depends on the size of your V, how deep is your V, and how wide is your well. Right? So this VA squared, which is sort of, you can describe a bit as the strength of the well. All right. So for a given gamma, how many of these cross points are there? And here's a formula that gives you the number of cross points, the number of allowed energies, the number of eigenvalue, and hence the number of eigenstates, and hence the number of wave functions, all the same. They're all 1 to 1 to 1, right? And here's a formula that gives that to you. Try to do that for homework. Try to prove that that's the case. I had to scratch my head. It was non-trivial. Maybe you're smarter than I am. You can see it immediately. All right. Okay. Now we start talking about delta wells, not just wells. All this is sort of revision. Well, this is a bit new. This is new, but most of it is revision. Now we start talking about delta wells, and a delta well. You take your square well, your finite square well with a finite potential depth, V naught, but you make that V naught become larger and larger, it goes to infinity. And at the same time, you're making the width of your well, your A, you're making it smaller and smaller, such that the product of A and V naught remains finite. Right? So in that sense, this well becomes a kind of delta well because it has the properties of a delta function, a la Dirac. Like it's similar to Dirac's delta function. Okay. All right. Now, so that's what I'm just saying here. Now, call this product of the width, A times the depth of the well, V naught. So call this product A V naught or V naught A. Same thing. Just call it delta, right? So, and this delta is less than infinity, so it's finite, right? So you make your well very, very tall and very, very thin So it sort of looks like this, right? So here's your V naught getting taller and taller, and your width here of your well A is getting smaller and smaller. So effectively, your well is looking like a spike, right? So such a well is called a delta well, right? So I guess that's fairly clear, right? Okay, so so we're defining this delta as the product of the width times the depth, right? V naught A.